Hey, welcome. Every single time you click a link or stream a show or send an email, you're basically launching this tiny messenger on a wild, high-speed journey across the entire planet. So today, we're going to follow that messenger and pull back the curtain on how the internet really works. What happens in that blink of an eye is pretty amazing.
I mean, seriously, have you ever stopped to think about it? In that tiny fraction of a second, this whole chain of events just fires off. It's like a perfectly choreographed dance of technology that stretches across continents. It's one of the most complex things humanity has ever built, and yet it happens so fast, we just take it for granted.
So, to make sense of all this, let's focus on the main character of our story today, a single packet of data. Just think of it like a tiny digital envelope, and inside is a little piece of your request. This packet is about to go on an absolutely epic quest, all the way from your screen to a server somewhere out there, and then all the way back.
Now you might be thinking, the internet is just this chaotic digital Wild West, where data is just flying everywhere. But it's actually the complete opposite. This whole journey is governed by a really strict set of rules, kind of like a digital roadmap that makes sure every single packet knows exactly where it's going and the best way to get there.
The foundation for that rule book, the sort of theoretical blueprint, is called the OSI model. It's a way of thinking about network communication by breaking it down into 7 different layers. It starts at the top with the application layer, the stuff you actually interact with, and it goes all the way down to the physical layer, the actual cables and radio waves. It's what makes sure all these different technologies can speak a common language.
Okay, so while that 7-layer OSI model is a fantastic textbook guide, what the internet actually runs on is a more streamlined version called the TCP/IP model. It basically takes those 7 layers and squishes them down into 4. This is the real-world workhorse model that's going to power our packet's journey today.
All right, our packet is ready to roll. So what's the first challenge? Just getting out of your house. Or, your local network. It needs to find the front door. And in the digital world, that front door is your router.
So every single device on your local network, your laptop, your phone, even your smart fridge, has a unique hardware ID called a MAC address. The best way to think about it is like a specific house number on your street. It's absolutely essential for devices on the same local road to find each other.
But wait, how does your computer find the MAC address of your router in the first place? Well, it uses something called ARP, the Address Resolution Protocol. Your computer basically shouts out a message to the entire local network saying, "Hey, I'm looking for the MAC address for whoever is using this IP address." The router hears this, and it replies with its MAC address. It's like a little local directory connecting the network address to the physical hardware.
So, our packet made it. It's at the router, standing at the end of the driveway, ready to hit that global highway. But its MAC address, its local house number, is totally useless out here. For this much bigger journey, it's going to need a whole new kind of address.
And now we're in the big leagues. Our little packet is leaving the quiet cul-de-sac of your home network, and it's merging onto the massive, sprawling superhighway of the internet, which connects millions and millions of other networks.
This is where the IP address comes into play. If the MAC address was the specific house number, the IP address is like the city and the zip code. It doesn't care about the specific device anymore. It just tells the internet the general neighborhood, the network, where our packet needs to end up.
The internet is this insane mesh of countless possible paths. So how in the world do routers pick the right one? Well, they use routing protocols. And you can just think of these protocols as the GPS of the internet. Routers are constantly talking to each other, sharing updates on traffic jams, closed roads, and new shortcuts, all to find the absolute fastest, most efficient path for our packet at that very moment.
And what's so cool about this is how they manage the scale. A protocol like OSPF, which stands for Open Shortest Path First, doesn't try to map the entire internet all at once. That would be impossible. Instead, it organizes the internet into these logical areas, which you can see here. This lets routers focus on their own little neighborhood and just know the best exits to get to other areas, kind of like our own highway systems.
So what happens if a router gets directions to the same place from 2 different GPS systems? It uses a clever trick called administrative distance. It's basically a trustworthiness score. And the rule is simple. The lower the number, the better. So a directly connected route, which has a score of 0, is always going to be trusted over a route learned from OSPF, which has a score of 110.
Okay, against all odds, our little packet has flown across the global network and it has arrived at the right server. But it can't just barge in the door. Before any data can actually be delivered, it needs to make a proper, secure introduction.
The IP address got our packet to the right building, the server. But which apartment does it go to? That is the job of the port number. You see, a server is running tons of different applications at once. Port 80 is the standard apartment for regular web traffic, or HTTP, while port 443 is for secure web traffic. This makes sure your request to see a website doesn't accidentally end up at the email server.
So how is the packet actually delivered? Well, there are two main ways. There's TCP, which is like certified mail. It's a bit slower, but it double checks to make sure every single packet gets there in the right order. Then there's UDP, which is more like a postcard. It's super fast, but it doesn't check for errors. For loading a web page, we need reliability, right? So we use TCP.
And the secret to TCP's reliability is this process, brilliantly shown here, the three-way handshake. Before your browser sends the actual request for the website, it has this quick little conversation with the server to make sure the server is there, listening, and ready to talk. And let's break it down, because it's actually really simple. First, your computer sends a SYN packet. That's like saying, hey, you there. The server replies with a SYN-ACK packet, which means, hi, yep, I'm here, and I hear you. Finally, your computer sends one last ACK packet, saying, awesome, okay, let's talk. And boom, the connection is established. And with that handshake complete, the server accepts our packet's request. It goes and finds the web page you asked for, breaks it into a bunch of new packets, and then sends them on the exact same epic journey, just in reverse, all the way back to your screen.
So let's do a super quick recap. Our packet used a MAC address and ARP to get out of the house. Then it used an IP address and routing protocols to navigate the global superhighway. And finally, it used a port number and a TCP handshake to deliver its message to the right application on the server.
But here's the part that just blows my mind. That entire journey, across cities, under oceans, through dozens of different pieces of hardware, following all these complex rules, the whole round trip typically happens in under 200 milliseconds. That is literally faster than you can blink your eye. And that really gets to the heart of it. The internet works because of agreement. It's not one single thing. It's a massive network of networks that have all just agreed to speak the same language, the language of protocols. The shared rulebook is the magic that allows for the seamless, instant communication we depend on every single day. So, from a simple click to a globe-spanning data exchange, all in less time than a blink. It's really a testament to decades of incredible engineering and collaboration. And it kind of leaves you with one last question to chew on. As this journey gets even faster and even more complex, what new possibilities is that going to unlock?